Hi, I'm Mark Barsamian with the Ohio University Math Department. In the previous video, we began our discussion of section 3.3 about segments and rays, with the definitions of segments and rays and some study of basic properties of them. In the current video, I'll discuss how rulers for lines dictate some of the important properties of segments and rays. This video is produced for Ohio University Math 3110-5110 College Geometry. Our topics will be discussing the coordinate description of rays and segments, the vector description of rays and segments in the Euclidean plane, and then we'll revisit Theorem 3.3.4 about equality of rays, and then finally we'll discuss the congruent segment construction theorem and midpoints of segments. This material is from section 3.3, Segments and Rays, pages 52 to 58, in the book Geometry, a Metric Approach with Models by Millman Parker. The corresponding homework for this video is this short collection of 5 exercises from section 3.3. There are some other exercises from section 3.3 in the previous video, video 3.3a. Let's recall some important stuff from previous sections. We discussed in section 3.1 using vectors to describe Cartesian lines. Given 2 distinct points, A and B, in R2, line AB can be described with vectors as follows. Line AB is the set consisting of points corresponding to vectors constructed in the following way. You take the point A, you think of it as a vector, and you put it here and here. You take the point B, and you think of it as a vector, and you put it here, and then you put a parameter t here. The collection of all of these such things, where t is a real number, those vectors correspond to points, the points that are on line AB. We also discussed in section 3.1 using vectors to describe rulers for lines in the Euclidean plane. A formula for a ruler for line AB is given by this. It's closely related to the expression describing line AB using vectors. And we discussed that this ruler is what's called a special ruler for that line. It's a ruler that has A as origin and B positive. That is, the ruler satisfies this. We discussed betweenness for points in a metric geometry. The definition of the sentence, B is between A and C, is the following. A, B, and C are collinear and distinct points, and the distances add up in this sense. In important theorem 3.2.3, we discussed that betweenness of points is related to betweenness of coordinates. So if 3 points have this betweenness relationship, then their coordinates will have this betweenness relationship on the real number line. We discussed existence of points with certain betweenness relationships. If you're given distinct points A and B in a metric geometry, then there exists a point C between them, and there exists a point D out beyond B. We discussed betweenness of 4 points, symbols like this. And then stuff from section 3.3 that was introduced in the previous video. The definition of a line segment. Segment AB, denoted that way, is this set. The set of all points such that C is equal to A, or C is equal to B, or C is between A and B. Definition of a ray. Ray AB, denoted by that symbol, is this set. The set of all points such that C is equal to A, or C is equal to B, or C is between A and B, or B is between A and C. Another way of thinking of it, maybe more helpful, is it is the union of segment AB with this additional collection of points. So now we'll start discussing some new material from section 3.3. The coordinate description of rays and segments is the first thing I'll talk about. We'll start with Theorem 3.3.5, which is about the coordinate description of rays. Now, it has a missing claim, which I've added, so it's, as I've presented it here, it's about the coordinate description of segments as well. So here's the theorem. Given distinct points A and B in a metric geometry, the claim is there exists a ruler, F, for line AB, such that the ray AB consists of all the points on that line that have a coordinate greater than or equal to 0. In other words, they are the preimage of this half-open interval from 0 to infinity. So I'll illustrate that claim before showing you the other claim. So in this picture, we're given these two distinct points A and B, and we can think about ray AB lying on line AB. And this theorem says there exists this coordinate function, this ruler, F, for that line with this property. The coordinate of any point that's on that ray will be a number that's greater than 0. Another way of saying that is this, that if I take the preimage of that half-open interval, then I get this ray. Now I said that there's a missing claim. The book doesn't present this theorem, but I wish they had. For that same ruler F, it'll be true that the segment AB consists of all the points on that line whose coordinates are greater than or equal to 0 and less than or equal to B. That makes sense because the segment AB will be here on that line, and the coordinates of those points will be here on the number line. Now there's a proof of this theorem in the book, and you actually, for a homework problem, will sort of try to clarify that theorem. The structure of that proof is not as clear as it should be. That's why I gave you that assignment. Now I'll give you a hint. Here are the headings for the major parts of the proof. Proof part 1 would be prove that if x is on the line AB and the coordinate of x is greater than or equal to 0, then x is in the ray AB. Proof part 2 would be prove that if x is on the line and the coordinate of x is negative, then x is not in ray AB. That's the proof for this first claim, the one that's printed in the book. Now I want to talk about a vector description of rays and segments in the Euclidean plane. This proposition, 3.3.3, is about the coordinate description of rays and segments in the Euclidean plane. Given distinct points A and B, ray AB and segment AB can be described as follows. Ray AB is this set of points that's corresponding to this collection of vectors. Point A gets interpreted as a vector and put there and there. Point B gets interpreted as a vector and gets put there. A parameter t gets put there. And the collection of all of these such points corresponding to vectors constructed that way, the collection of all of those with the property that t is greater than or equal to 0, that collection is ray AB. The collection of all points corresponding to vectors like this, where t is a number between 0 and 1, that corresponds to segment AB. Now I'm going to illustrate the statement of this proposition, but not yet. I'm going to first talk about how we'll prove it. Okay, there are a bunch of typos in this paragraph. So I've fixed, I think, what I needed to fix in this paragraph. It's a mess. When I post this collection of notes to the web, I will fix this so it's typed the right way. But here's what it was supposed to say. Notice that proposition 3.3.5, which is about the coordinate description of rays and segments. Let's go up and look at that. That's this proposition. Notice that that proposition is numbered after proposition 3.3.3 about the vector description of rays and segments in the Euclidean plane. That's the thing that I want to discuss now. But nothing in proposition 3.3.3 got used in the proof of 3.3.5. And in fact, it would have been better for the authors to put 3.3.5 first, because it can be used to make the proof of proposition 3.3.3 simple. And so that's what I'm going to do here. I'm going to prove proposition 3.3.3, and I'm going to use some of the results from proposition 3.3.5. Usually you can't do that. You usually can't use a later numbered theorem to prove an earlier numbered theorem, because it might be a circular kind of reasoning. You might have used the earlier theorem to prove the later theorem, and then you're going to use the later theorem to prove the earlier theorem. But that's not the case here. There was nothing in the result of proposition 3.3.3 that ever got used in the proof of proposition 3.3.5. So we're going to use the proposition 3.3.5 result to prove proposition 3.3.3. So here's how we'll prove proposition 3.3.3. Now remember what that proposition says. It says that ray AB in the Euclidean plane equals this set, the collection of points that correspond to this vector constructed this way. Put point A there and there, put point B here and here, put a parameter t there, and require that t be greater than or equal to 0. The claim is that that collection of points corresponding to vectors constructed that way, that collection of points is ray AB. So here's the proof. So let AB be a ray in the Euclidean plane. Now by earlier proposition 3.1.4, we know that we can build a ruler for that line AB using this vector equation. We take point A, we put it there and there. We take point B and put it here, and then we have a parameter here. Remember, every one of these things corresponds to a point on that line. So this formula is telling us what the coordinate of that point on the line is going to be. The coordinate is going to be obtained by doing this calculation. We discussed that ruler back in the video for section 3.1. So we have this ruler, and furthermore, we discussed in exercise 3.1.5 the fact that that's a special ruler. It has A as origin and B positive. So by the result of proposition 3.3.5, there's that later numbered proposition, we know that ray AB can be expressed in terms of its coordinates this way. Ray AB is the set of all the points on that line AB whose coordinate is greater than or equal to 0. Well, in our situation, our coordinate function is this. So that means that we can use that coordinate function, and we know that the points whose coordinate will be greater than or equal to 0 will be, well, the points on that line, that is the points corresponding to vectors constructed that way, with the property that their parameter t is greater than or equal to 0. So in other words, ray AB is the set of points that correspond to vectors constructed this way. We got a point A there and there. We got a point B there, and we have a parameter t here with a property that t is greater than or equal to 0. That's what we were supposed to show. We were supposed to show that ray AB was the set of points corresponding to these vector operations. So we've proven this part of the theorem, this part of the proposition. Now for proof part 2, we're supposed to prove the claim about segment AB. That is, that segment AB is the set of points corresponding to vectors constructed this way, where t is greater than or equal to 0 and less than or equal to 1. Now the proof of part 2 would be very similar to part 1, so I won't do that here. Now that we've done the proof of this proposition and realize that it involves coordinates, I want to go back and illustrate the statement of this proposition. So there you see an illustration of sort of how this proposition was proven, and also sort of illustrates what it says. That the points on this ray AB, can be constructed as using this vector operation, and those points would be points whose coordinates, using that special ruler, are numbers that are greater than or equal to 0. Here's the t-axis. I'm using the parameter t, not x. So the points on this ray, using that special ruler, will have coordinates that are greater than or equal to 0. Let's go on. Now that we've learned about the coordinate description of rays and segments, we can use those descriptions to prove some important facts. But first, before proving those important facts, we should take a moment to revisit a theorem that was introduced in the previous video, but whose proof was postponed. We had this theorem 3.3.4 about the equality of rays. This theorem was about some subtlety in the notation for a ray. And the second part of this theorem was fairly straightforward. If two rays are equal, then their initial points are equal. We proved that in the previous video, just using the concept of extreme points of a ray. But the proof of this first part of the theorem, let me illustrate that. The first part of the theorem says, if point C is an element of ray AB, and C is not equal to the endpoint A, or the initial point A, then ray AC, this red ray, is the same ray as ray AB. So in other words, there are different symbols that can represent the same ray. These two symbols represent the same ray. So that's easy to visualize, but in the previous video, we did not discuss a proof of it. I said at the time we would postpone the proof until we knew about the coordinate description of rays. Now that we know about that, we can do the proof of this. So here's the proof. Suppose we have a point C on ray AB, and C is not equal to A. Well then, either C is between A and B, or C is equal to B, or B is between A and C. That's by statement 1 and the definition of ray. Now, we can let F be a special ruler for that line that has A as origin and B positive. Now, we know that such a ruler exists by Theorem 2.3.2, that is the ruler placement theorem. We know that given two distinct points, there's a special ruler for those points. Now, since that betweenness relationship, or this equality, or this betweenness relationship is true for the points, we know that either that betweenness relationship, or this equality, or this betweenness relationship is true for the numbers that are the coordinates of those points. That's by Theorem 3.2.3, that important theorem about the relationship between betweenness of points and betweenness of the coordinates of those points. But then we know that either this inequality is true, or this equality is true, or this inequality is true. Now we know that by what we said in statement 4, that we have these three relationships, but also because we know that A is origin and B is positive. That is, f of A is the number 0, and f of B is some positive number, so f of B has got to be greater than f of A. So that's how we know that these inequalities go this way. So observe that in every one of these cases of statement 5, in this case, and in this case, and in this case, in all three of those cases, the coordinate of C is a positive number. And also note that line AB and line AC are actually the same line. So that ruler that was introduced back in step 3, this special ruler for line AB, could also be thought of as a ruler for line AC, with A as origin and C positive. So this this f is also the ruler that's mentioned in Theorem 3.3.5. Remember that theorem said that this ray could be written as this set, the set of all points on the line whose coordinate is greater than or equal to 0. Well, that's the same as this set, the set of all points on line AC whose coordinate is greater than or equal to 0. And that's just what this symbol means, ray AC. So this is kind of a very simple way of proving that ray AB equals ray AC. We used coordinates. We used coordinates for the line to prove that those two rays were the same ray. So that's why I postponed proving this theorem from the previous video. That's why I postponed proving it until this video. Let's go on. Now, as I mentioned a few pages ago, now that we've learned about the coordinate description of rays and segments, we can use those descriptions to prove some important facts. The first of these is this theorem, Theorem 3.3.6, the congruent segment construction theorem. It says this: given a ray AB and a segment PQ, there exists a unique point C on line AB that makes this true. Segment AC is congruent to segment PQ. Let me illustrate this. So the theorem says, given this ray and given this segment, there exists this unique point C such that this segment AC is congruent to this segment PQ. There's a nice proof of this theorem in the book. It uses the coordinate description of rays. I won't discuss the proof, but I will discuss this example that illustrates that theorem. In the Poincare plane, let P be this point and Q be this point, and let A be that point and B be this point. Question A says, find the point C on ray AB that makes a segment AC that's congruent to segment PQ. Well, here's how you do that. First of all, we have to find the length of segment PQ. So to do that, we need to find the distance between P and Q. Now observe that P and Q have the same x-coordinate. They both have an x-coordinate of -15. So the Poincare line that contains those 2 points is the type 1 line, denoted that way. That should say this. So on that line, we use this distance formula. The distance between these 2 points in the Poincare plane is the absolute value of the logarithm of the ratio of their y values. So that's a mouthful, but when I do that and I use their y coordinates, I get this. ln of 2 is the distance from P to Q. Now we have to get a special ruler for Poincare line AB. Now A and B do not have the same x-coordinate, so the Poincare line that they lie on is a type 2 line. Because of this, we'll need to find the center and the radius for that line. If you do the calculation, you find the center is the number 4, so 4, 0 are the xy coordinates of the center, and the radius r is the number 13. That's a special triangle, a 5, 12, 13 triangle. Using these, we construct the standard ruler for the Poincare line using that old formula, and we get that the standard ruler is this. Now we need to figure out if that standard ruler is a special ruler. So we compute the coordinate of A using that ruler, and we find that the coordinate of A is 0. We compute the coordinate of B, and we find the coordinate of B is ln of 5. So with that standard ruler, the coordinate of A is 0, and the coordinate of B is positive. So in other words, this ruler that we built, the standard ruler, is a special ruler. So now we can use that theorem. Theorem 3.3.5 says all the points C on that ray AB will have a coordinate f of C greater than or equal to 0. But we want a particular point C. We want point C to satisfy this equation, the distance from A to C, the Poincare distance, has to equal the Poincare distance from P to Q. The Poincare distance from A to C is normally given by that ugly Poincare distance formula, but we can use the ruler equation. It tells us that the distance between A and C is equal to the absolute value of the difference of their coordinates. And we have a special ruler, so the coordinate of A is 0, and the coordinate of C we know is going to be a positive number. So this whole calculation is just going to equal coordinate of C. Now we have a known value for the distance PQ. A while ago we found that the distance from P to Q was a number ln of 2. So we know that that's got to be the result of finding the coordinate of point C. So we use the ruler. Here's this special ruler that we built. The ruler for that line AB is that ruler. And we set that result of that calculation equal to ln of 2. So we have this equation that the xy coordinates of point C have to satisfy. They have to satisfy this coordinate equation in order for the distance from C to A to be the same as this distance from P to Q. So I call that the coordinate equation. But point C also has to satisfy this circle equation because it's on line AB. And that circle equation has to have C equals 4 and R equals 13. So we have two equations in the two unknowns, x and y. There's this equation that guarantees that C is the correct distance from point A. And there's this equation that guarantees that C is on that circle. If we solve those two equations, we find that C has these coordinates, 59 over 5, 52 over 5. Question B is to illustrate our solution to A. Well, here's our point P, negative 15, 7. Here's our point Q. Here's our point A. Here's our point B. And here's our point C. Notice that this segment and that segment are the ones that have the same length, so I should label that. So the distance between P and Q is ln of 2. The distance between A and C is ln of 2. Notice that this type 1 line, we know, is the type 1 line denoted negative 15L. This is a type 2 line on the right. It centers at 4, 0, and its radius is 13. So this is the line denoted that way, 4L13. Notice that I've labeled the center of that semicircular shape, and I've labeled the missing endpoints with their xy coordinates. The missing endpoints are down on the x-axis, so their y coordinates are 0. All those points have y coordinate 0. These points are 13 units apart because that circle has radius 13. Let's go on. The last subject I want to talk about is midpoints. As I mentioned many pages ago, now that we've learned about the coordinate description of rays and segments, we can use those descriptions to prove some important facts. I said we were going to prove 2 important facts. Well, the second of these important facts has to do with midpoints of segments. Here's the definition of a midpoint. To say that M is a midpoint of segment AB means that M is a point that satisfies both of these requirements. M lies on line AB, and the distance from A to M is the same as the distance from M to B. Now we can illustrate this. There's an illustration of a segment with its midpoint. Now notice that I've drawn the midpoint so that it's between the endpoints of the segment. In one of your homework exercises, you have to prove that. If M is a midpoint of segment AB, then M is between A and B. The key to proving this fact is to consider possible locations of M on line AB relative to A and B. So M could be here, or here, or here, or here, or here. 5 possibilities for its location in relation to those points. Here, or here, or here, or here, or here. The key is to show that in any of these cases, that one, or that one, or that one, or that one, the resulting distances AM and MB cannot be equal. The way to do that is to use a ruler for line AB and to make that argument. So therefore, the only possibility that's left is that one. That's how you'll prove that. You'll also prove the following theorem in another homework exercise: the existence and uniqueness of the midpoint of a segment. It says this: if A and B are distinct points in a metric geometry, then segment AB has exactly one midpoint. Now here are some hints for proving this. Let F be a ruler for line AB, a ruler that has A as origin and B positive. Now remember, you have to cite references for justifications. We can say that such a ruler exists by the ruler placement theorem. You should look up the number of that, though. So we have a ruler that has the property that f of A is 0 and f of B is greater than 0, some number greater than 0. That's the first hint. The second hint is to then guess what the coordinate f of M would have to be. I'm going to leave that to you to guess. I think you should think back to what you know about midpoints of segments from previous courses and think about how that would show up in our course with the terminology and notation of our course. I think you can come up with a guess for what this coordinate would have to be. Now check to see that if M does have that coordinate that you guessed, then M will indeed have the qualifications to be called a midpoint. So that will prove that a midpoint exists. Now there's another issue of uniqueness of a midpoint. I won't discuss this in the video, but I will discuss it in our meeting. That's the end of the video. Thank you.